Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions from May June 2023 Paper 4 Variant 1. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of A2 physics and also you can have better understanding of these questions. Let's study together, let's improve together. In today's lesson, we are talking about May June 2023 Paper 4 Variant 1. Total time for this exam is 2 hours and you need to answer all questions on this paper. And total mark for this paper is 100. On second page of your exam paper, you can find values of some important constants, and if you need value of any constant in your exam for calculations, you can come to this page and you can find values of constants. And also you can find some basic formulae. These are formulae from ES physics. Maybe you will need some of them for some basic calculations for A2 physics as well. So if you need, you can come to this page and you can find some basic formulae. On next page, formulae for A2 physics are given to you. If you have forgotten any formula and you want to double check, you can come to this page and you can double check. So these are some basic formulae from A2 physics, but these are not all the formulae you need for A2 physics. Question 1, part A says define gravitational field, and gravitational field means G. This is simply equal to gravitational force per unit mass. So simply we can write down this is gravitational force. Better you can say gravitational force per unit mass. Gravitational force per unit mass. If you write down force per unit mass, still you will get mark. This question has only 1 mark and this is B mark. Mean this has to be in your answer. For the second part, we need to define electric field, and electric field is defined also in a very similar way as we have defined gravitational field. Electric field simply is equal to electrical force per unit positive charge. So this is F per unit positive charge. Positive charge is very important because we use this convention to define the electric field or to define direction of electric field. Use unit positive charge. So you have to write down per unit positive charge. So this is how direction of electric field is defined. We can also imagine in this case, let's say we have this electric field. So this one is the electric field. So this is electric field. So in this case, we are drawing these lines pointing downwards. So this means this side is positive, this is positive, this is positive. So here negative, negative, and negative. And if we place a positive charge inside this field, we can find out direction of the field. I mean, this positive charge will experience force downward. So that's the reason these arrows, they are pointing downwards, because direction of electric field is defined by unit positive charge. So the unit positive charge is very important. You have to mention this one in your answer. So how we can define electric field? So simply you can say electric field is electrical force per unit positive charge, per unit positive charge. So this is how you need to define electric field for A2 physics, per unit positive charge. And this question has 1 mark and this is B mark. Mean this one has to be in your answer. Third part says state one similarity and one difference between the gravitational potential due to a point mass and electric potential due to a point charge. First of all, let's try to understand what is gravitational potential. Gravitational potential is equal to negative capital G capital M divided by R. So M is the mass and R is the distance from the point mass. From here we can see that potential is inversely proportional to distance from the point mass. And also we need to understand at infinity potential is defined as 0. So at infinity potential is equal to 0, or simply you can say at infinite distance from the point mass potential is equal to 0. Now let's try to understand electrical potential. Electrical potential is equal to K capital Q divided by R. If this Q is positive, so the potential will be positive, meaning the potential due to positive charges is positive, and potential due to negative charges. So here we have negative charge, this is divided by R. So potential due to negative charges is negative. So very important point, this is the difference between gravitational potential and electric potential. From here we can also see that V is inversely proportional to the distance from the point charge. So V is inversely proportional, and gravitational potential is also inversely proportional to distance from the point mass. At infinity, electric potential is also defined as 0. At infinity, we can say potential is equal to 0. So these are the points you need to understand to answer this question, but for this question you have to write down one similarity and one difference. So we can see at infinity, both of them they are 0. So this is one similar point, so this is also 0. Both of them they are inversely proportional to distance, so this is also similarity. But gravitational potential is always negative because gravity is attractive force, but electric potential, it can be positive, it can be negative depending on sign of the charge. Now let me show you the answer, how you can write down your answer. So in your answer you have to mention these points. So the first point, if you write down inversely proportional to distance from the point mass, or it can be the distance from the point charge if you are talking about electrical potential. So if you write on this one point, you will get 1 B mark. You can write on this point, or you can write down this one, 0 at infinite distance, you will get 1 mark. If you have written gravitational potential is always negative and electric potential can be positive or negative, you will also get 1 mark, but you have to write down these 2 points. It can be positive or negative depending on sign of charge. So you need to understand why when it can be positive, when it can be negative, depending on sign of charge. So we can write down depending on sign of charge. So if you write down these points, you will get 2 marks. Part B says an isolated uniform conducting sphere has mass capital M and charge capital Q. The gravitational field at the surface of the sphere is small g and electric field at the surface of the sphere is capital E. So we can imagine we have one small sphere. Then the distance from the center of the sphere to the surface is capital R. And value of G at the surface is given, that is equal to small g. This one has to be equal to G capital M divided by R square. And value of E at the surface means capital E. This one has to be equal to K. Capital Q means the Q at the surface of the sphere divided by distance from the center of sphere. Now the question is that how we can use these 2 equations to get this one. If you look at this given equation, you can see we have here G over E, and we need to show that M over Q is equal to alpha times G over E. So it simply means that I will divide this G by this because I can see in the equation G divided by E. So first of all, I will write down here G divided by E, and G is equal to G capital M divided by R square. E is divided, so here we will have R squared divided by K times Q. From here R square we can cancel with R square, so simply we left with G capital M divided by K times Q. But we need to show that M over Q is equal to alpha times G over E. So we can rearrange this one. We can write down G over E. This one is equal to G over K. And here we have this is M over Q. So if we rearrange, we can write down M over Q. This one has to be equal to K times small g divided by capital G capital E. But for K we need to understand K is equal to 1 over 4 pi epsilon naught. So this is K. So we can plug in here. So G divided by 1 over 4 pi. So it means we will have here 4 pi epsilon naught capital G, and we will have capital E. Now if we rearrange this one, we can write on here. So this part, this is a constant. So this is constant, and this constant we can replace with alpha. So here we have G divided by capital E. So this is what we need to prove. Means m over q, this is equal to alpha times g over E. So this is what we need to prove, this one. And alpha here we can write on alpha. Alpha is equal to 1 over 4 pi epsilon naught times capital G. So this one is alpha. So this is value of alpha. For the second part, we need to show that numerical value of alpha is equal to this. And alpha, we derived the expression for alpha. Alpha is equal to 1 over 4 pi epsilon naught times capital G. Now simply we need to plug in values. So we can write on 1 over 4 pi epsilon naught. Epsilon naught is equal to 8.85 times 10 to minus 12. And value of G is 6.67 times 10 to minus 11. Now simply you need to use calculator and you will be able to get 1.35 times 10 to 20 kg square per coulomb square. So this is our final answer. If you have got this right answer, you will get 1 mark. This question has only 1 mark. And this is answer mark. Part C says, assume that the earth is a uniform conducting sphere of mass 5.98 times 10 to 24 kgs. The surface of the earth carries a charge of negative 4.80 times 10 to 5 coulombs that is evenly distributed. Use the information in B to determine the electric field at the surface of the planet. Give a unit with your answer. In the last part, we have already discussed that m over q, this is equal to alpha times g over capital E. And if we cross multiply, we can write down m times E. This will be equal to alpha times capital Q times small g. And from here we can write down E. This is equal to alpha times Q times G divided by capital M. Now simply we need to plug in values. Alpha, in the last part we have discussed, alpha was equal to 1.35 times 10 to 20. And value of Q is given to us here. So this is 4.80 times 10 to 5. We are only interested with magnitude, so no need to add this negative sign here. Times value of G is equal to 9.81. Now simply we need to divide this one by capital M. Capital M is given to us, that is equal to 5.98 times 10 to 24. And if we solve this one, our answer should be equal to 106 up to 3 SF newtons per coulomb, because electric field, this is equal to force per unit positive charge. So the unit of electric field is newtons per coulomb. And this question has 2 marks. The 1 mark you will get if you have plug in these values. You will get 1 C mark, and you will get the answer mark if you have got the right answer. So this question has 2 marks. For the second part, we need to state how the direction of the electric field at the surface of the earth compares with direction of the gravitational field. So first of all, we can imagine this is our planet. So this is our planet, and direction of the gravitational field is pointing towards the planet. So this is pointing towards the planet. So this is the gravitational field. So we are simply talking about M. Gravity is attractive force. Now we need to also define direction of electric field. So now we can imagine our planet. It has a negative charge Q. So this is negative charge Q. So direction of electric field also has to be towards this charge, negatively charged sphere. So direction has to be towards. So it means if our planet is negatively charged, direction of electric field and direction of gravitational field, they are the same. So you can simply write down here same direction, because charge is negative. If charge was positive, directions will be opposite, as charge is negative. So gravitational field and electric field, they have the same direction. So simply we can say same direction. same direction. So the answer for this question is simply you need to write on the same direction, and this question has 1 mark, so this is B mark. That's all for today's lesson. I hope this video was helpful, and I'll be uploading remaining questions very soon. See you in next video. Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions from May-June 2023, Paper 4, Variant 1. In the last video, we have already discussed question 1 about gravitational field. Today's lesson, we will start from question 2, and we will try to cover all questions about mechanics and thermal physics. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of A2 physics, and also you can have better understanding of these questions. Let's study together, let's improve together. Question 2 says a steel sphere of mass 0.29 kg is suspended in equilibrium from a vertical spring. The center of sphere is 8.5 centimeters from the top of the spring as shown in figure 2.1. The sphere is now set in motion so that it is moving in a horizontal circle at constant speed as shown in figure 2.2. The distance from the center of the sphere to the top of the spring is now 10.8 centimeters. For part A, we need to explain with reference to the forces acting on the sphere, explain why the length of the spring in figure 2.2 is greater than in figure 2.1. A beautiful question, a conceptual question. So read question, try to think about forces acting on the sphere in figure 1 and forces acting on sphere in figure 2, and then compare. So that's all what you need to do. So first of all, if you look at figure 1, in this case we have sphere. So if we draw the free body diagram, force acting downwards on the sphere, this one has to be mg, and force acting on the sphere upwards, this one has to be the tension T. And in this case, in the second case, there is also tension here, so we can draw this line here. So there is also tension is acting along this line, so we can say this one is T. Now if you look at this one, on the sphere there is a one force that is acting down, that force is mg. But this tension has two components. So one component of the tension, this angle is 27, so here angle, this angle also has to be 27 because alternate angles are equal. We can resolve this T into two components. So we can also draw one line here, so we can say this is horizontal component of tension, so this one is TH. And horizontal component of tension in this case is providing the centripetal force, so we can write down this one is FC. Horizontal component is providing centripetal force because this is moving in a horizontal circle. So in this case we can simply write down T is equal to mg. T is equal to mg. For this one, so you can see this is a triangle, so if you wanna draw an other line here, you can also draw the line here. So this is a triangle, so we can draw the arrow here. If you are more curious about this one, you want to see this one in a proper way, we can draw another line here. So this is vertical component of tension, so we can say this one is TV vertical. So this is also TV, I just draw here so you can see how forces are balanced. So in this case, along vertical we can say T vertical, this one is equal to mg, and T horizontal in this case is equal to centripetal force. So if we want to write down T here, T has to be equal to T vertical square plus T horizontal square and root of this. T vertical is equal to mg square, so this is mg square, means T vertical square, plus T horizontal, we have this is centripetal force square and root of this. So this is new value of tension. I can say this one is T nu, and we can say this one is T naught. T naught, you can say this is equal to mg, so we can write on here. So we have T naught square plus we have fc square. I hope now you can see from here it is very clear to you that T nu, this one is greater than T naught. So T nu in this case is greater than T naught because extra force provided by the spring is centripetal force. So spring in this case also is providing the centripetal force, means the horizontal component of tension in the spring is providing centripetal force. So that's the reason T nu is greater than T naught. If tension is greater, it means extension for the spring. If tension in the spring is greater, so let's write on here, if tension in the spring is greater, then spring has spring constant, so delta x also has to be greater because this is constant. If this increase, this also has to increase. So that's all what you need to understand in this way. If these concepts are clear to you, so let me show you the answer, how you can write down your answer. So you can write down these points in your answer. First point you can mention in this case, horizontal force on sphere causes centripetal acceleration. Mean horizontal force on sphere, this one is providing the centripetal force. And this is the horizontal component of tension. Weight of the sphere is now equal to vertical component as we have mentioned here, and greater tension in the spring, so greater extension of spring. So if T greater, it means delta x also has to be greater. I hope this makes sense to you. Part B says the angle between the linear axis of the spring and vertical is 27 degrees. So this angle is given to us, so we can also write down 27 here because alternate angles are equal. For part B1, we need to show that radius r of the circle is 4.9 centimeters. So it means that we need to show that this radius of the circle, this is equal to 4.9 centimeters. 4.9 centimeters. We have L is given, that is equal to 10.8 centimeters. So simply we need to understand this triangle. So we can form this triangle and we need to find out base of the triangle. So in this case, base of the triangle, this base is equal to r and this has to be equal to L sine of, because this angle is 27, so opposite side has to be sine, so this has to be sine of 27 degrees. L is 10.8 centimeters. So simply we can say r in this case has to be equal to L sine of 27 degrees. L we have, that is equal to 10.8 centimeters multiplied by sine of 27 degrees. So our final answer in this case will be 4.9 centimeters. Pretty straightforward one. Simply you need to understand how to form the triangle, then how to solve the triangle. For the second part, we need to show that tension in the spring is equal to 3.2 newtons. But we have already discussed forces acting on the sphere. We have discussed that mg is acting downwards on the sphere and the tension is acting on sphere along this certain angle. And we can resolve this tension into two components. We have discussed it as one vertical component. So this one is the vertical component and it has one horizontal component. So this one is the horizontal component. We can also complete this triangle for better understanding. So we can complete this triangle. So in this case, this is vertical component. An angle is given to us. Here we have angle. This angle is 27 degrees. So if this angle is 27 degrees, so this component of the tension, this has to be T cosine of 27 degrees because this is with angle. And this one will be T sine of 27 degrees because this is opposite to the angle. And so this component is T cosine of 27 degrees. this sphere is in equilibrium, it means forces along vertical they are balanced, but sphere is moving in a circle, in a horizontal circle, so it means forces along horizontal are not balanced. So the resultant force on the sphere is this one, and this force is providing centripetal force. But for this case we need to find value of tension only, so we can look at forces along vertical. Along vertical we have T cosine of 27 degrees. This one has to be equal to mg. So from here we can write on T, this has to be equal to mg divided by cosine of 27 degrees. So here we have m, that is equal to 0.29 kgs, and value of g is 9.81 divided by cosine of 27 degrees. If we solve this one, we will get T is equal to 3.2 newtons up to 2 SF. So this is how you need to answer this question. This question has 2 marks. The first mark you will get if you have written this equation, you will get 1 C mark even if your answer is wrong. But if you got the right answer, you will get 2 marks. Third part says the spring obey Hooke's law. Calculate the spring constant in newtons per centimeter of the spring. So we need to calculate K. So in this case, delta T, the increase in tension, this one has to be equal to K times delta X. We need to calculate value of K, so simply we can say K has to be equal to delta T divided by delta X, and delta T has to be equal to new value of T minus initial value of T divided by delta X. So from here simply we can write down T new. We have new value of T that was equal to 3.2 newtons, and initial value of T, if you look at this figure, initial value of T is equal to mg. So here we have initial value of T, so this one is T naught, and T naught, this is equal to mg, means mass of the sphere times g, and mass of the sphere is 0.29 multiplied by 9.81. And new value of spring we have, that is equal to 10.8, and the initial value of L for the spring we have, that is equal to 8.5, and the unit of this one is centimeters. So if we solve this one, we will get 0.15 newtons per centimeter. So this is our final answer, and this question has 2 marks. The first mark, C1 mark, if you have written this part, so you will get 1 C mark, and the second mark is the answer mark. If you got the right answer, you will get 2 marks. Part C1 says use the information in B to determine the centripetal acceleration of the sphere, and centripetal acceleration, this one has to be equal to the centripetal force divided by mass of sphere. So centripetal force we have already discussed actually, so let me redraw. We have discussed the forces acting on the sphere, mg is acting downward, and tension is acting at certain angle in this direction. So this one is the T, and this tension has 2 components. One is the horizontal component and one is the vertical component. So this one is the vertical component, and we have the value of angle here is equal to 27 degrees. So this is the T. This horizontal component is providing the centripetal force, so this is T sine of 27 degrees. So simply we can replace centripetal force in this case with T sine of 27 degrees, because centripetal force is equal to this 27 degrees divided by mass of the sphere is 0.29, so T is 3.2 newtons. So here we have sine of 27 degrees divided by 0.29. Now if we solve this, our answer should be equal to 5.0 meters per second up to 2 SF. So this is our final answer, and this question has 2 marks. If you have written this step, you will get 1 C mark, and if you got the right answer, you will get 2 marks. For the second part, we need to calculate the period of the circular motion of the sphere. So we have centripetal acceleration, so we can start with centripetal acceleration. Centripetal acceleration is equal to r times omega square, but omega is equal to 2 pi over t, means the angular velocity is equal to 2 pi over t. Now simply we can replace omega with 2 pi over t, and if we simplify this one, we will get this is r, and here we have this is 4 pi square over we have T square, and here we have AC. We can rewrite here, so we can say A, this is equal to 4 pi square, and here we have R divided by T square. For this question we need to calculate time period, so we need to make T the subject. So we can write down here, so this is 4 pi square R divided by A, and this is T square, so this is T square is equal to this, but we need T, so we will take root on both sides. So here we will get, this is 2 pi, and here we will get R divided by A. Now simply we need to plug in values of R and A. A is the centripetal acceleration and R is the radius of the circle. Radius of the circle is equal to 0.049 meters, or you can say 4.9 centimeter, divided by 5.0. This is value of acceleration. Now simply we need to solve. If we solve this one, we will get 0.62 seconds. So this is the final answer, 0.62 seconds. And this question has 2 marks. 1 mark you will get if you have written this expression, you will get 1 C mark, and if you got the right answer, you will get 2 marks. Question 3 part A says, state the reason why 2 objects that are at the same temperature are described as being in thermal equilibrium. Let's try to understand this one with one simple example. Imagine that we have object A and this object is hot, and we have another object and this object is cold, and we can say this object is B, and they are at 2 different temperatures. So in this case, thermal energy will flow from hot to the cold object. Let's say this is 100 joules of energy. Some thermal energy from cold object will also flow to the hot object. Let's say this is 20 joules of energy. So in this case, there is net flow of energy from the hot object to the cold object. So it means that in this case, cold object is gaining thermal energy, so its temperature will rise. Now we can imagine a case when these 2 objects, they are at the same temperature. So we can say this is our object A now, and this is our object B. They have reached the same temperature. So let me clean this one. So they have reached the same temperature now. So this is object B. So this one is hot and this one is also hot, but they are at the same temperature. So delta T is equal to 0. So in this case, it doesn't mean that there is no thermal energy transfer when they are at the same temperature. When they are at the same temperature, there is no net thermal energy transfer, but still thermal energy will flow from A to B. Let's say this one is 60 joules of energy. Then from B to A, when they are at the same temperature, same amount of thermal energy will flow from this B to A as well. So in this case, A and B, when they are at the same temperature, they are in thermal equilibrium because there is no net thermal energy transfer between these 2 objects. So this is what is meant by thermal equilibrium. No net transfer of thermal energy between 2 objects when they are at the same temperature. I hope this one is clear to you. Now let me show you the answer. So this is how you can write down your answer. If you write down this one sentence, you will get 1 mark, and this is B mark, mean it has to be in your answer. Part B says figure 3.1 shows the variations with temperature of the densities of mercury and of water between 0 degrees Celsius and 100 degrees Celsius. Temperature may be measured using the variation with temperature of the density of a liquid. Suggest why for measuring temperature over this temperature range, mercury is a suitable liquid and water is not a suitable liquid. So first of all, we will look at this graph. If we look at this graph, we can see this graph is linear. If this graph is linear, so first thing we can say this one is linear. So one thing we can say about this graph, this one is linear. But if you look at this second graph, this graph is non-linear. So this one is non-linear. This one is linear, and also it has unique value of density at each temperature. So here we have one value of temperature, one value of density, and if we pick another point, let's say if we pick this point, at this point it has certain value of temperature and it has certain value of density. It simply means that each value of density is unique at certain temperature. So this graph is suitable, means mercury is a suitable liquid to measure temperature, but this is not a suitable one. If we draw a horizontal line here, so we can see at the same value of density we have two values of temperature. So that's the reason this is not a suitable liquid for measuring temperature. And at this point you can see we have two values of temperature and we have one value of density, and also this is non-linear, so this is not suitable liquid. So these 2 points we have to mention, and this has 1 mark and 2 marks. Let me show you how you can write down your answer. So in your answer you can talk about these points. First one has only 1 mark. If you write down variation of density with temperature is linear, you will get 1 B mark. You can also say each temperature has a unique value of density, you will get 1 B mark. And for the second one, water is not a suitable liquid, you can say variation of density with temperature is not linear, as we have mentioned here is non-linear. Region where the density does not vary with temperature means at this point density is not vary too much with temperature. So you can also talk about this region. We can also say different temperatures have the same density, as we have mentioned at this point. We have one value of temperature, at this point we have another value of temperature, but the density is the same. So that's the reason water is not a suitable liquid. So this is how you can read the graph. You need to understand how to read the graph and how to get informations from the graph. So this question is all about reading graph. Part C says a beaker contains a liquid of mass 120 grams. The liquid is supplied with thermal energy at a rate of 810 watts. The beaker has a mass of 42 grams and a specific heat capacity of 0.84 joules per kg per Kelvin. The beaker and the liquid are in thermal equilibrium with each other at all times and are insulated from its surroundings. Figure 3.2 shows the variation with time t of the temperature of the liquid. For part C1, we need to state the boiling temperature in degrees Celsius of the liquid. So if you look at given graph, so we have the liquid, so we increase temperature of the liquid, then temperature of the liquid stays constant. So it means here this point is the boiling point, because here phase is changing, so we can say this one is the boiling point. And temperature at this point simply we can read from y-axis. From vertical axis we can read temperature, and temperature in this case this is 75, so this will be 77.5 and this one will be 80. So let me write down here, so this one is 80 degrees Celsius. So simply you have to write down 80 degrees Celsius, and this is B mark, mean it has to be in your answer. Part 2 says determine the specific heat capacity in joules per gram per Kelvin of the liquid. So we need to determine C for the liquid. We can say C for the liquid. This has to be equal to Q supplied to the liquid, means thermal energy supplied to the liquid. So we can say thermal energy supplied to the liquid divided by M times delta T, the rising temperature. So in this case Q liquid we don't have, so we can leave that part. And mass of the liquid we have, beaker contains liquid of mass 120, so we can write down this is 120 grams. And rising temperature we have from 25 to 80, so we can write down 80 minus 25. So we need to find out Q liquid, but in this case we can find out Q total. Q total has to be equal to Q supplied to the liquid, so we can write down Q supplied to the liquid plus Q beaker, and thermal energy used to raise the temperature of the beaker. We need to find out in this case Q liquid, so we can rearrange. We can say Q liquid, this has to be equal to Q total minus Q beaker. So this is beaker. So Q total we can find out because we have the time and we have the power. Power is given to us. So it means P times T. So we can write down 810 watts multiplied by 21. This is the time. And Q for the beaker, this one has to be equal to mass of the beaker, MP, C for the beaker, times the rise in temperature of the beaker. So here we will have 810 times 21 minus mass of beaker 42 gram. So we have 42 grams multiplied by C. C for the beaker we have, this is 0.84. Be careful with the unit. So this is given in joules per gram per Kelvin. So it means this can be gram. But if it is in kilogram, you have to convert this one into kilogram. So we have C, and the rise in temperature we have, that is 80 minus 25, because beaker and liquid, they are in thermal equilibrium, they are at the same temperature. So this is value of Q supply to the liquid. Now simply we need to write down here. So we will be writing here 810 times we have 21 minus we have 42 multiplied by 0.84 times we have, this is 80 minus 25. So we can use double bracket here. Now if we solve this one, we can find out value of C for the liquid, and this one has to be equal to 2.3 joules per gram per Kelvin. So our answer is 2.3. A beautiful question, how to answer questions about thermal capacity, means specific thermal capacity. A beautiful question. Part D says the experiment in C is repeated using water instead of the liquid in C. The mass of the liquid used, the power supplied, and initial temperature are unchanged. The specific heat capacity of water is approximately twice that of the liquid in C. The boiling temperature of water is 100 degrees Celsius. On figure 3.2, sketch the variation with time t of the temperature of the water between t is equal to 0 and t is equal to 60 seconds. Numerical values are not required. So first of all, if you look at the graph, we have temperature and time. Temperature on y-axis and time on x-axis. So we can write down the gradient. Gradient of this one has to be equal to the change in temperature, delta theta, divided by change in temperature. We can say this is delta T. For this one, specific heat capacity is given to us. So we can write down Q has to be equal to MC delta theta. Power is constant, so we can write in Q in terms of power, mean P times T, or we can say P times delta T. Interval of time, thermal energy is supplied. So we can say this is P times delta T. So here we have MC delta theta. C is given to us in this case. So we can write on this one in terms of C. We can say this is P divided by M, and here we will have delta T divided by delta theta. Now if we compare this part with the gradient, we can simply write down, in this case, C is equal to P divided by M times 1 over gradient. So this is the main point. So delta T over delta theta, this is equal to 1 over gradient. For this question, it is given to us C for water, this is double. If this is double, this one has to be half. So this has to be half. So we can write down here, gradient of new line, it has to be half. So it has to be half. So this is the main point. So let me circle this one. So this is the main concept you need to sketch line. Gradient has to be half. Now we will look at the same interval of time. Mean here we have the same interval of time until here. If the gradient is half, it means the rise in temperature has to be half. So if you look at the previous line, so here we have the final temperature, this one is 80. So the rise in temperature, you can also see we have one big square, we have another big square, and we have two small square here. So half of that. So we have 10, this is 10, 20, 22. So 11 means until here. Until here. So if we choose this point on the line, that line should have half the gradient. Now simply we need to connect this one by the straight line. So we will start from here and we can connect this point and just draw the straight line connecting that point. So it is here. So this is the boiling point of water, and after that it has to stay constant. So this is how you need to draw the line. So the main concept is this: gradient has to be half. So first of all, I have found this one, gradient has to be half. If gradient has to be half, for the same interval of time, change in temperature has to be half. So here we have found change in temperature is half, then we have drawn just straight line, and when it has reached the boiling point, temperature after that has to be constant. So beautiful way to answer. Try to do this one again if once it is not clear to you. Very good question to practice graph. Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from May-June 2023, Paper 4, Variant 1. In the last two videos, we have already discussed about gravitational field, simple harmonic motion, and thermal physics. In today's lesson, we will talk about second law of thermodynamics, we will talk about capacitance, and if we have more time, we will also discuss about electromagnetism. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of A2 physics, and also you can have better understanding of these questions. Let's study together, let's improve together. Question 4 part A says, state two of the basic assumptions of the kinetic theory of gases. Kinetic theory of gases we also call KMT. So we need to state two basic assumptions of KMT. The first basic assumption, we can say particles are in continuous random motion. So we can say the first one, particles are in continuous random motion, and the second one we can say particles we can write down in a little bit different way. So we can say volume of the particles, we can write down in a beautiful way. We can say volume of the particles is negligible, means very small as compared with volume of gas, or we can say as compared with volume of container is very small. What exactly it means? It simply means that imagine that we have this is one container and this container is filled with gas. So there will be gas particles moving randomly. Let's say we have these gas particles. So this is the volume of the gas. Now if we take all these particles and we place them in one corner, so we will have these 5 particles here. So the volume of the particles itself is negligible as compared with volume of the gas. So this is the second assumption. You can also write down this one in a little bit better way. So let me rewrite this one. So this part I want to show you so you can have some feelings about that. You can simply imagine if I take all these 5 particles together, I can simply place them here. So we have one particle here, we have one particle here, one particle here, one here, one here, means just close to each other. So the volume of the particle is negligible as compared with volume of the gas. So this is the second point. And the third point is forces between molecules are negligible. So we can say negligible forces between particles. We can also write down in detail between particles. You can also say between molecules, except collision. It simply means that these particles, they're moving. When they're moving, there are no forces between particles. But when particles collide with each other, that time they exert forces on each other. But before collision, there are no forces among particles. So this is the third assumption we can write down. And the fourth one, we can say all collisions are perfectly elastic. Collisions are perfectly elastic, means no loss of kinetic energy. Perfectly elastic, no loss of kinetic energy. So these are 4 basic assumptions, but for this question simply we need to write down 2 of them. So let me show you how you can write down your final answer. In your answer, you can choose any two of them. So in a proper way, you can say particles are in a continuous random motion. So continuous random motion is very important. Particles have negligible volume compared with the gas volume itself. Negligible forces between particles except during collisions. All collisions are perfectly elastic, mean no loss of kinetic energy. So you have to write on only two of them. Part B says an ideal gas has amount of substance small n. The gas is initially in state X with pressure 2p and volume V. The gas is cooled at constant volume to state Y with pressure P. The gas is then heated at constant pressure to state Z with volume 2V. Finally, the gas returns at constant temperature to state X. For part B1, we need to determine an expression for the temperature of the gas in state X in terms of N, P, and V. Identify any other symbols that you use. If you look at state X, for state X it is given to us the volume of the gas. So imagine that we have gas here, and volume of the gas for state X is given is V, and the pressure of the gas is 2p. So we can write on here the pressure of the gas is equal to 2p. So we need to write on expression for the temperature of the gas. So simply we have to use ideal gas equation PV. This is equal to nRT. So from here we can say temperature. This will be equal to PV divided by N times R. P in this case is equal to 2p. So this one is 2p, and here we have volume. This is divided by N times R. Simply we can say we have here this is 2PV divided by NR. So this is the expression for temperature. But in this case we have used this constant R. So we need to state what is R. R is molar gas constant. So you have to write down this is molar gas constant. Molar gas constant. So if you have written this equation, you will get 1 mark, and this one is C mark. And if you have got the right answer and you have written molar gas constant, you will get another mark, and this is A mark. If your answer is correct, you will get 2 marks. Second part says on figure 4.1, sketch the variation with volume of pressure for the gas as gas undergoes theory changes. The state X is labeled states Y and Z. Now if you look at the given states, we have state X. For state X, it is given to us value of P is means the pressure is 2P and the volume is V. So we can write down V comma 2P. Now if you look at state Y, for state Y it is given to us volume remains constant and value of pressure is P. Volume remains constant, so means we have V and we have pressure that is equal to P. Next one is state Z. For state Z it is given to us the gas is then heated at constant pressure, means P remains constant with volume 2V. So we have volume here 2V and pressure is P. For the final state it is given to us isothermal, temperature remains constant. So this is isothermal process between Z and X, ZX. Between Z and X, this process is means between two states Z and X, process is isothermal, means temperature remains constant. And isothermal process, this is important one, this step you need to understand. Isothermal process, it means that temperature remains constant, so PV is equal to constant. So isothermal, PV is equal to constant. So this is coming from here, means PV, this is equal to nRT. If temperature is constant, R is also constant, N is also constant, it means PV is equal to constant. So it also means that P and V, they are inversely proportional to each other. Inversely proportional. So P and V, they are inversely proportional to each other. Very important point. We need this one to sketch the curve. Now we have state X, then we have state Y, volume remain constant. So at this point is state Y, volume has to be V, pressure has to be P. Then we have state Z, volume has to be 2V. So it will be somewhere here 2V, and pressure has to be constant. And finally we have isothermal, means inversely proportional. P and V, they are inversely proportional to each other. So this will be hyperbola, kind of rectangular hyperbola. So this is how you need to sketch the final curve. So let me clean this one, and this is our final answer. I hope this one is clear to you. So this has to obey PV is equal to constant, because this is isothermal process. Third part says during the change of state from Y to Z, the increase in internal energy of the gas is capital U. During the change of state from Z to X, the work done on the gas is W. Complete table 4.1 to indicate for each of the three changes of state the increase in internal energy of the gas, the thermal energy transferred to the gas, and work done on the gas in terms of PV, U, and W. So for this one, first of all, we need to understand first law of thermodynamics. According to first law of thermodynamics, delta U is equal to Q plus W, and this W is the work done on gas. Work done on gas will be positive and work done by gas will be negative. So let me rewrite here. Work done on gas is equal to negative of work done by gas. So this is very important. Work done on gas will be positive if the gas is compressed. So we can say if the gas is compressed, work done on gas will be positive. If the gas expand, work done on gas will be negative. And work done, we can calculate W is equal to P times delta V. If it is compressed, work done on gas positive. If the gas expand, work done on gas will be negative. Now, based on this knowledge, we can answer this question. And one thing more we need to understand. Delta U is equal to 0 if delta T is equal to 0. As in this case, we have from Z to X, means in this process, delta T is equal to 0. It means that delta U is also equal to 0. From Z to X, so delta U has to be equal to 0. Now we also need to understand in any cyclic process, the second point, in any cyclic process mean in one complete cycle, delta U also is equal to 0. So it simply means that if we start from state X, we go to state Y, then we go to state Z, then we again come back to state X, the same state. So it means the change in temperature is equal to 0. If change in temperature is equal to 0, it means delta U is equal to 0. Now we have Y to Z, delta U, this is positive, and this one has to be negative. So here we can simply write down this one has to be delta U negative, because if we add all of them, the sum has to be equal to 0. So if this is positive, this is 0, this one has to be negative. Now the second thing, if you look at from X to Y, X to Y, we can see the volume remains constant. As volume remains constant, means W, this also will be 0 if delta V is equal to 0. So between X and Y, delta V 0, it means work done on gas, this is equal to 0. Now we have to apply first law of thermodynamics for this process X to Y. So we have delta U, that is equal to minus U, and we have work done, that is equal to 0. So how about thermal energy? So here we can write down this one. We have, this is delta U. We don't know this one, but we have this one, that is equal to 0. So how about here, thermal energy transfer to the gas, that also has to be negative U. So we can write down here negative U. If you go to Z to X, so we have change in internal energy, that is equal to 0, and work done on gas is plus W. So if we write down the first law of thermodynamics, so let me use different color. For Y to Z, for Y, Z to X, we are talking about Z to X. What is delta U? Delta U is equal to 0. What is work done? That is W. How about Q? Sum of these two has to be equal to 0. So this one has to be negative W. Now only we left Y to Z process. And so in this case we have internal energy, but work done we can calculate from here. So from here we can calculate work done. So we can write on W, we are talking about Y to Z, W has to be equal to P, means the pressure here times the change in volume. In this case, volume is increasing. If the volume increase, gas expand, so work done on the gas has to be negative. So we can say work done on gas, this one has to be negative. So we have P here, this one has to be negative. How about the change? We have 2V minus V, so here we have 2V minus V, so we will get V here. So this is work done by gas, so we will get positive, but work done on gas has to be negative, because work done by gas is equal to negative work done on gas. So we have here, this is negative PV, so we can update here, this one has to be negative PV. Now we need to calculate thermal energy. So the last one, for this one we can use a different color. We can say from Y to Z, we can write down first law of thermodynamics, mean this law again. We have delta U here, that is equal to U. First of all, we can write down this is plus U. We need to calculate thermal energy transfer to the gas, and plus we have work done, that is equal to negative PV. So here we need U here, U, so Q should be equal to U minus PV. This has to be U plus PV, yes, U plus PV, because it has to be cancelled. Minus we have here, so this is PV. So now you can see on both sides we have U. So in this case, this is cancelled, this is cancelled. So what is over Q here? U plus PV. So we can simply write down here, this one has to be U plus PV. So this question is simply, you need to understand few points. You need to understand how to calculate work done by gas, and work done by gas is negative of work done on gas. So this is one point you need to understand. You also need to understand how to use first law of thermodynamics. You also need to understand delta U is equal to 0 if delta T is equal to 0. And also you need to understand in any cyclic process, mean if one complete cycle, delta U is 0, because for the same state delta T is equal to 0. So this is how you need to answer. Question 5 says part of an electric circuit is shown in figure 5.1. The circuit is used to produce half wave rectification of an alternating voltage of potential difference V in. The output PD across 14 kilo ohm resistor is V out. For part A1, a component is missing from the circuit of figure 5.1. Complete the circuit diagram in figure 5.1 by adding the circuit symbol for the missing component. Correctly connected. Very important. Correctly connected. So this is half wave rectification. So it means we can use single diode. So we have to use single diode. So we need to draw the symbol for the single diode. So this is how we can draw the symbol for diode. But if you leave like this, it means this one is wrong. So you have to draw this line. So this has to be a complete line. If you draw like this, for example, as I explained you before, if you draw like this, it means you will lose marks, because they have specified correctly connected. So it has to be connected with this wire. So this is how you need to draw. For the second part, it is given to us a capacitor capital C is shown in the circuit of figure 5.1. State the effect on V out of including the capacitor in the circuit. The purpose of capacitor in the circuit is smoothing. So we can say smoothing. So if we have capacitor in the circuit, V out will be more smooth. So we can say V out is smooth. It will be more smooth, means the variations in V out will be small, or we can say ripples in the V out will decrease. Part B says figure 5.2 shows the variation with time t of V in, means the V input. And if you look at one complete cycle of V in, so this should be one complete cycle. So this is how we can draw. So this is one complete cycle of V input. So the time period of V in is equal to 0.04 second, because the unit of this one is second, unit of time is second. Question says figure 5.3 shows the variation with t of V out. in the last part we have discussed that time period of V in. Time period of V in is equal to 0.04 second. Now how about time period of V out? Time period of V in and time period of V out has to be the same. So very important point, you need this one for your exam. So the time period of T out means the output, time period of output also has to be the same. So we can say T V out. So the time period is equal to 0.04 second. Let me explain you this one in a proper way. This is half wave rectified. So this is half wave rectification because we are using single diode. So this is half wave rectification. So this is first thing we need to understand how half wave rectified signal will look like. So this is how half wave rectified signal will look like. So let me draw with this color. So this is half wave rectified signal. We can also draw the blue line here. So this is our half wave rectified signal. In this case we have a capacitor. So you can see for this half of the cycle there is no V out. So capacitor will start discharging. So in this interval of time our capacitor will discharge. So you need to understand here capacitor is discharging. Capacitor discharges. And here from this point to this point capacitor is charging. So you can say from here to here capacitor charges. So we can say capacitor charges. And again from this point to this point capacitor discharges. So capacitor discharges. So the time period in this case is equal to 0.04 seconds. So frequency of V in, this has to be equal to 1 over T. And T we have that is equal to 0.04 seconds. It means this is 100 divided by 4. So we will get this is 25 Hertz. So the final answer is 25. Second part says show that the time constant for the discharge of the capacitor through the resistor is 0.038. So first of all we need to understand where capacitor is discharging. Capacitor is discharging between these two values of PD. And we can find out those two values of PD if we read from y-axis here. So this PD is 5.50. Then also we can draw an other line here and we can read from y-axis, and this one is 3.25. So we have value of V naught and we have value of V. And also we can read discharging time from here. Discharging time is equal to 0.02 second. So we are talking about discharging of capacitor. So we need to understand V as a function of time is equal to V naught e to the power of minus t divided by RC. RC is time constant. Vt we have the value of this one is 3.25. Mean value of PD across capacitor after time 0.02 second is equal to 3.25, and initial value of PD is 5.50. So here we have e to the power of minus t and t is 0.02 seconds, and this is divided by RC. We can simplify this one. We can write on here. We have 3.25 and this is divided by 5.50. And here we have e to the power of negative 0.02 and this is divided by RC. Now if we take natural log on both sides, we can say ln of 3.25 divided by 5.50. This is equal to negative 0.02 times we have this is divided by, so this is divided by RC. So this is divided by RC. So from here we can find out RC value. If we solve this one, take log of this one and we cross multiply, we can find RC. So let me write down a little bit in detail. So in this case we can write down RC. This one will be equal to negative 0.02 and this will be divided by ln of 3.25 divided by 5.50. So now simply you need to use calculator, and if you solve this one, your answer should be equal to 0.038 second. Then RC, this is the time constant. So here we have 0.038 second. So this is our final answer. And this question has 2 marks. If you have got the right answer, you will get 2 marks. But if your answer is wrong, you have written this equation, you will get 1 mark. So always when you start answering any question, write down the equation, then plug in values and then calculate the final answer. Third part says calculate the capacitance of capacitor capital C. Give a unit with your answer. But in the last part we have just calculated time constant, that is equal to RC. Now we need to calculate value of C. So simply C is equal to tau divided by capital R. R is the resistance of resistor in the discharging circuit. Value of tau is 0.038 and the resistance of resistor is 14 kilo ohms. Now if we simplify this one, we will get 2.7 times 10 to minus 6 farad. So this is the unit of capacitance. So we have to write down 2.7 times 10 to negative 6, and the unit is farad of capacitance. Unit of capacitance is farad. Part C says the circuit of figure 5.1 is modified so that it produces full wave rectification of an input voltage. Suggest with a reason how V out is now varies with time when V in is as shown in figure 5.2. So now is full wave rectification. So we can write down full wave rectification. So we have full wave rectification. Full wave rectification simply means that this negative becomes positive. So this just flip, negative becomes positive. So we will have constant value of V out. V in we have, this one is the V out. We label this one so you will not get confused with V in and V out. So this one is our V out now. This is V out, and our V in is the same as it is shown here, means this is our V in. So we can draw here, this one is our V in. So you can see the comparison. That's the reason I want to draw this. So this one is our V in. So this blue is representing V in and the red is representing V out. So this one is V in. I hope you can see the difference between V out and V in. So simply we can say here, this one is constant now. So this is constant. Now let me show you the answer, how you can write down your answer. In your answer, you can mention these points. You can say V in has constant magnitude in both positive and negative direction. Mean this positive direction of V in, this one you can see it has a constant value, and negative also has a constant value. So you can mention this 1 point, this has 1 mark, B mark. Then V out is positive. So let me draw again. So this is our V out. So this one you can see, this one is V out, and this is constant. And that's all for today's lesson. I hope this video was helpful and you have improved your understanding of capacitance, and also you have improved your understanding of first law of thermodynamics. If this video was helpful, please like and subscribe, and also leave some comments in comments section. Then also if you have any questions, you can ask in comments. That's all for today lesson. I'll see you in next video very soon, and next video will be coming by tomorrow. Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from June 2023, paper 4, variant 1. In the last few videos, we have already discussed from question 1 to question 5, and today's lesson, we will start from question number 6. We will talk about electromagnetism, we will also discuss about quantum physics, and we will also talk about medical imaging. Especially, we will discuss a beautiful question on ultrasound. Let's study together, let's improve together. Question 6 part A says, state what is meant by a magnetic field. Magnetic field simply is a region around a magnetic pole, or we can say around a moving charge, or simply we can say around a current carrying conductor, means current carrying wire. If in that region we bring another magnetic pole, or we bring another moving charge, or we place a current carrying wire in that region, wire or current carrying conductor will experience a force, and that region we call is magnetic field. Let me show you the answer, how you can write down your answer. This is how you can write down your answer. In your answer you have to mention a region where a force acts on a magnetic pole. You can also say force acts on a moving charge, or you can say force on current carrying conductor. So any one of them you can mention in your answer. And this question has 2 marks. First mark is the M mark. You must have written a region where a force acts on, and then if you write down magnetic pole, or if you write down moving charge, or if you write down current carrying conductor, you will get 2 marks. Part B says a long straight wire P carries a current into the page as shown in figure 6.1. On figure 6.1, draw 4 field lines to represent the magnetic field around wire P due to current in the wire. So first thing we need to understand, this current is into the page. We have current and we need to find out direction of magnetic field. So simply we can write on here, we have current and we need to find out magnetic field direction. So we need to find out magnetic field direction. So we have one quantity and we need to find out direction of another quantity. For that purpose we have to use right hand grip rule. So simply we will write down here which hand you have to use. We have to use right hand grip rule. So this is, we need to use right hand grip rule and right hand grip rule. So this is my right hand. You can see current in this case is into the page. So like this, current is into the page. So the magnetic field is clockwise. So magnetic field is clockwise. So I can write down here magnetic field is clockwise and current is into the page. So clockwise. So you have to draw lines clockwise. So let me show you how you can draw the magnetic field. So this is how you can draw the magnetic field. But one thing you have to be very clear, the gap between the lines, mean this gap, it has to increase, it has to go on increasing. Actually this question is asking you to draw 4 field lines. I have already drawn 3 here. We can also draw another one. We can also draw another one like this. So these 4 field lines, this is how you need to draw 4. But one thing we have to be very clear, as I mentioned before, the gap, this has to increase. You see this gap is shorter, this gap is wider, and this one is the widest. This is telling us that magnetic field, as we go away from the wire, magnetic field get weaker and weaker. So this has to be in your answer. Part C says a second long straight wire Q carrying current of 5.0 amps out of the page is placed parallel to wire P as shown in figure 6.2. The flux density of the magnetic field at wire Q due to current in wire P is 2.6 millitesla. Calculate the magnetic force per unit length exerted on wire Q by wire P. Exerted on wire Q. And it is also given to us the magnetic field due to wire P near Q, we can simply say BP. This is equal to 2.6 millitesla. We can say BP. We need to calculate force. So magnetic force means the force on Q. This will be equal to BIL. For this question, we need to calculate magnetic force per unit length. So simply we can write on here F on Q by P divided by L. This is equal to BI. But here is one very important point we need to understand. We are talking about force on Q. So we have to consider magnetic field due to P, external magnetic field. So if I write on here, so this one is the external magnetic field. So external magnetic field here is due to wire P, and this is current in wire Q. Now simply we need to plug in values. We have magnetic field due to P at Q, that is 2.6 millitesla. 2.6 times 10 to minus 3, and value of current in wire Q. In wire Q, the value of current is 5.0 amps. So we can write down this is 5.0 amps. Now if we multiply this one, we will get 0.013 newtons per meter. So this is our final answer up to 2SF. And this question has 2 marks. The first mark you will get if you have written this formula. For writing this formula, you will get 1 C mark. And if you have got the right answer, you will get an other mark. If your answer is correct, you will get 2 marks. But if your answer is wrong, but you have written the formula, you will get 1 mark. Second part says state direction of the force exerted on wire Q by wire P. So we have to consider the force on Q by P. So let's try to understand the formula first of all. So F is equal to BIL. So we need to understand which magnetic field we have to consider. So we need to consider the external magnetic field, means magnetic field due to P, and we need to consider current in Q, and L has to be the length of Q. Now if you look at wire P, current for wire P is given, that is into the page. So the magnetic field at this point due to P, this will be downward. So this is the magnetic field. So you can use your right hand. So if you turn your fingers, if you curl your fingers, you will see magnetic field at this point is down, and current in this wire is out of the page. So now you have to use Fleming left hand rule. Fleming left hand rule. So if we use Fleming left hand rule, we have magnetic field that is down, and we have current that is out of the page. So we can write on here, we have B, this one is down, and we have current that is out of the page. So the force will be to the right. So this is one way you can find out direction of force. Another way to find direction of force is, as current in this wire is into the page and current in this wire is out of the page, these two currents, they are in opposite directions. It means these two wires, they will repel each other. So the force on this wire will be to the right, and force on wire P will be to the left. But for this question, simply we need to find direction of force on wire Q. So simply we can say this is to the right. Third part says the flux density of the magnetic field at wire P due to current in wire Q is 1.5 millitesla. It simply means that we have BQ, and BQ is equal to 1.5 millitesla. For this question, we need to determine the magnitude of current in wire P, and also we need to explain reasoning. In order to answer this question, the first thing we need to understand, whenever we have two wires and they carry current, force on each wire is the same in magnitude but opposite in direction. It simply means that if we write down here force on P due to Q has to be equal to force on Q, and these two forces, they have the same magnitude but they are in opposite directions, and this is based on Newton's third law. So simply we can say it is based on Newton's third law. So this is the reasoning. Question was asking you explain your reasoning. So this is our reasoning. Now simply we need to use F is equal to BIL. F is equal to BIL. We need to determine, in this case, current in the wire, but in the last part we have already calculated force per unit length. force per unit length. So simply we can say this is equal to Pi. This P is the external magnetic field, mean this is due to Q, and I is current in P. So this value we have already calculated, and that was equal to 0.13. So here we have BQ and here we have IP. For this question we need to calculate value of IP. So simply this will be equal to 0.013 divided by BQ, magnetic field due to Q, and we have here that is 1.5 millitesla. So we have 0.013 divided by 1.5 millitesla. If we solve this one, we will get our final answer is 8.7 amps. So this is current in wire P. So simply we can say 8.7. And this question has 2 marks. The first mark you will get if you have written the first statement, and this is the B mark, I mean this one has to be in your answer. And the second mark is the answer mark. If you have got the right answer, you will get 2 marks. Question 7 part A says, state what is meant by de Broglie wavelength. De Broglie wavelength simply is equal to H divided by P, or we can say this is H divided by M times V. It simply means that if P is very small, lambda will be very long, means it will be detectable. For example, for electrons, wavelength is detectable. But for human beings, as the mass of human beings is very high, it means lambda is very short, and that is not detectable. That's the reason we appears like a particle. But mass of electron is very small, and electron can be detected by different experiment like electron diffraction. We can observe electron behaves as a wave. So simply we can say wavelength associated with moving particles. So this is simply you can write down, and if you write down in your answer you will get 1 mark, and this is B mark. In your answer you have to write down moving particle, because if V0 it means lambda will be equal to 0. So you have to mention moving particle. Part B says figure 7.1 shows a glass tube in which electrons are accelerated through a high potential difference to form a beam that is incident on a thin graphite crystal. So here we have thin graphite crystal. After passing through the graphite crystal, the electrons reach the fluorescent screen. The screen glows where the electron strike the screen. Figure 7.2 shows the fluorescent screen viewed end on from the right hand side of figure 7.1. State the name of the phenomenon demonstrated by the pattern shown in figure 7.2. So in this case we can say if electrons they behave as a particle, we should see only electrons right in front of this beam of electron. We should see electrons here, means we can expect electrons here. But in this case electron they spread out. So it simply means that this is demonstrating electron diffraction. So this is diffraction. So in our answer simply we can say this is electron diffraction. For the second part we need to explain what can be concluded from the pattern in 7.2 about the nature of electrons. So in this case electrons they diffract, and only wave can diffract. Diffraction is a property associated with waves. So in this case electrons are behaving as wave. So this is we can write down for the second part. So for the second part we can simply say beam spreads out indicating diffraction. So electron beam is behaving as a wave. So if you write down these 2 points you will get 2 marks. Part C says the electrons in B are now accelerated through a greater potential difference between the cathode and anode. On figure 7.1, sketch the pattern that is now seen on the fluorescent screen in figure 7.1. So in this case potential difference has been increased, so it simply means that the kinetic energy of electrons will increase. So here we can write down kinetic energy. If potential difference increase, it means kinetic energy will increase. And kinetic energy we can write down in this form. We can write down P squared divided by 2m. So this is Q times delta V. We can simply derive this one. So this is very simple derivation. We can derive this. Simply what you need to do is kinetic energy is equal to 1/2 mv square, and momentum, this is equal to mv. From here we can get value of v. We can say v is equal to p divided by m. And now if we plug in this one back inside here, we will get p squared divided by 2m. From here we can write down p. This will be equal to 2m times q times delta v, root of this. So you can see here, if potential difference increase, it means momentum will increase. Now we can write down de Broglie wavelength. This is equal to Planck's constant divided by momentum of particle. So if momentum of particle increase, it means lambda will decrease. If lambda decrease, it means spacing decreases. Spacing decreases. So we can say spacing decreases. So rings are close to each other. So we can say rings get closer. So rings get closer. Now let me explain you this one with one simple example as well, with the help of diagram. You can see here, so this is the diagram, and you can see we have another diagram here. This is at low speed, this one is at higher speed, means these rings are close to each other. So now we need to draw the rings on this one, but they have to be close to each other. So simply you can draw like this. So this is very important point. Most of the time they will ask you in the exam. For the second part, we need to explain with reference to de Broglie wavelength the change in the pattern on the fluorescent screen. Actually, we have discussed this point in the last part. Let me recap some important points. We have discussed that momentum is equal to 2m times q times delta v. Delta v is the potential difference. So if delta v increase, it means momentum of the particle will also increase. Then lambda has to decrease because h is the Planck's constant. If momentum increases, wavelength has to decrease. If wavelength decreases, it means the fringe spacing, it has to decrease. If we are using the same graphite crystal, mean same grating spacing. If you're using, or simply we can say if you're using the same graphite crystal with the same grating spacing, diffraction angle will decrease, or simply we can say fringe spacing will decrease, as you can see here. So this is at low PD and this one is at high PD. So we can see this spacing, this decreases. So these are the points you have to write down in the answer. Let me show you the answer. In your answer, you can mention these points. First of all, you can say greater PD. It means greater momentum, as you can see from this first point. Second, greater momentum, so decrease in de Broglie wavelength. So you can say greater momentum, decrease in de Broglie wavelength. Smaller de Broglie wavelength for the same grating spacing, means if you're using the same graphite crystal, causes smaller diffraction angle, mean fringes will be close to each other, or you can say decrease in fringe spacing. In diffraction pattern, mean fringes will be close to each other. So these points you need to write down. These are kind of standard points, so it's good to master them. You can start with this one, momentum, then you can go to lambda, then you can say if lambda is small, fringe spacing will decrease. Question 8 part A says table 8.1 shows some data relating to the properties of air, gel and body tissue. The data are given to 3 significant figures. For part E1, we need to show that specific acoustic impedance of gel is 1.68 times 10 to 6 kgs per meter square per second. Acoustic impedance, we use letter Z for acoustic impedance, and this is the product of density of medium times speed of ultrasound in that medium. In this case, we are talking about gel. Density of gel is 1200 and the speed of sound in gel is 1400. If we multiply this one, we will get 1.68 times 10 to 6 kgs per meter square per second. So this is the answer. For the second part, we need to complete the table 8.1 by calculating the missing values to 3 significant figures. Use the space below for any working that you need. So if you look at this table, we have here density is given to us, speed of sound is given to us, and acoustic impedance is given to us. For the first row, for air, we need to calculate density of air. And density of air simply will be equal to acoustic impedance divided by speed of ultrasound in air. So Z we have, this is equal to 440 divided by 340. We will get 1.29, 3 significant figures. So we can write on here 1.29. For the second part, for gel, we need to calculate Z. We need to calculate acoustic impedance. Z is equal to rho times C. Actually, we have already calculated here. So we can write on here, this will be equal to 1.68 times 10 to 6. Same, we have already calculated. So we can say this is 1.68 times 10 to 6. And for tissue, we need to calculate C. So we can write on C for tissue. C for tissue will be equal to acoustic impedance divided by density of tissue. Acoustic impedance is equal to 1.68 times 10 to 6. Simply we need to divide this one by its density, that is 1090. And if we solve this one, we will get 1540 meters per second. So this is the speed of sound in tissue. So we can write on here 1540 meters per second. So this is how we can answer. Simply for this part of the question, you need to understand this formula. Simply you need to understand this. You need to understand acoustic impedance is the product of density of the medium times speed of sound in that medium. Part B says use the information in A to calculate the intensity reflection coefficient for A tissue boundary and for gel tissue boundary. For A tissue boundary, we can use alpha sub r. It means we are talking about intensity reflection coefficient. This is equal to Z1 minus Z2 square. Z is representing acoustic impedance divided by Z1 plus Z2 square. So we are talking about air and we are talking about tissue. So we have, for tissue, we have value of Z, that is equal to 1.68 times 10 to 6, minus for air we have 440. So this is 440, then square of this, divided by Z1 plus Z2. So we have 1.68 times 10 to 6 plus we have 440 square of this. And if we solve this one, our answer will be very close to this value. We will get 0.999. So what this is representing, if value of alpha is equal to 0.999, means it's very close to 1. It means that most of the ultrasounds, they will be reflected back. So they will return back into air. So this is the meaning of 0.99. And this question has 2 marks. The first mark you will get if you have entered these values, means you will get the C mark here, and the final is the answer mark. If you got the right answer, you will get this mark. Means 1 mark is for writing the formula, 1 for calculations. And so in this case, if the ultrasound are traveling from air, so let me draw here. So let's say this is the air, and here we have the tissue. In this case, ultrasounds coming here, most of the ultrasound will be reflected back, most, and very little it will enter the tissue. So this is meaning of 0.999. Gel tissue boundary, we need to use the same steps, but we have just different numbers. So we can write down alpha r for this one, means intensity reflection coefficient. Again, we can write down the formula, Z1 minus Z2 square. Always write down the formula, divided by we have Z1 plus Z2 square. We are talking about gel tissue, so we are talking about gel, we are talking about tissue. For the gel, we have this is 1.68. For the tissue, also 1.68. So we have 1.68 times 10 to 6 minus 1.68 times 10 to 6 square of this one divided by, we have 1.68 times 10 to 6 plus we have 1.68 times 10 to 6 square of this, and if we solve this one we will get 0 divided by this. So we have divided by 1.68 times 10 to 6 plus we have 1.68 times 10 to 6 square of this one. So in this case we will get 0. So it simply means that reflection is 0. So if we try to understand this one with the help of diagram, we can say these are the incident ultrasound waves and these are the ultrasound waves. They will enter the tissue. So in this case, as alpha is 0, it means all the ultrasound they will enter the body tissue. So this is what we want, and that's reason we use gel on the body, on the belly of moms for better results. Very nice question. So you need to understand why do we use gel, because we want most of the ultrasound to enter the body and contribute to image formation. Part C says use your answers in B to explain why gel is applied to the skin during ultrasound scanning. Actually, we have discussed this point in detail. Why do we need to apply gel? So you can see here we have, this is ultrasound. So this is ultrasound transmitter, and you can see gel here on the belly of patient. So why do we use this gel? We have discussed this point in detail in the last part. Now I will again highlight some point and then we will be able to write the answer. The reason is that because gel and the body tissue, they have same acoustic impedance. So they have almost same acoustic impedance. Means same value of Z. If same value of Z, it means that alpha R, intensity reflection coefficient, this is close to 0. So it simply means that most of the ultrasound, they will enter the body of the patient and they will contribute to the image formation, and we can have better image and we can easily see details of the parts of the body inside the body. So these are the points we need to understand, and this question has 2 marks. So in this case, let me rewrite one thing again. So if this one is the gel and this one is the tissue, here we have the tissue, and if Z is the same, in this case most of the ultrasound waves, they will enter the tissue, because in this case alpha R is close to 0. So we can get better image, so we can study the internal body parts in more detail. So let me show you the answer, how you can write on your answer. So in your answer you have to mention these 2 points. The first point, you can say without gel almost all of the incident ultrasound is reflected from the skin. So we can draw here, for example, if no gel, then here is air and here is tissue. We have done calculations, you can check the previous part. So in this case most of the ultrasound will be reflected back, very little will enter the body. So in this case we cannot get a better image, so image will be blurry, we can say blurry, and here we will get clear image. So we will get clear image. So this is one point you can write down. With gel we can say almost all of the incident ultrasound is transmitted into the body, so we will get clear image. So that's all for today's lesson. I hope you have better understanding of electromagnetism, you have better understanding of medical imaging, and also you have better understanding of quantum physics. So that's all for today's video, and if this video was helpful, please like and subscribe, because your encouragement is very important. I'll see you in next video. Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from June 2023 paper 4 variant 1. Today's lesson, we will start from question 9, and question 9 is about nuclear physics. We will also discuss question 10, and question 10 is about astronomy and cosmology. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of these topics, and also you can have better understanding of these questions. In the previous videos, we have already discussed from question 1 to question 8, and for the solution of those questions you can check the channel and you will find the solution of question 1 to question 8. Let's study together, let's improve together. Question 9 part A says define half-life. This is very common definition from nuclear physics, so you need to understand how to define half-life in a proper way. And this question has only 1 mark. Half-life, simply we can say average time taken. Imagine that the activity of a sample is A, and this activity after certain period of time becomes half. So the average time taken for activity to become half, this time we call is the half-life. We can also understand this one. Let's say we have n number of nuclei of any sample, and after certain period of time, half of the nuclei they decay, and time taken in this case, that average time taken also is equal to half-life. We can also write down this one in terms of mass. Let's say we have mass of a sample is capital M, and after certain period of time, half of the mass decays into an other element. That time taken also is the half-life, means that average time taken, that is also the half-life. So this is how we can define half-life. Let me show you the answer, how you can write down your answer. For the answer of this question, simply you need to write down average time taken for activity of sample to become half. If you have written this one, you will get 1 mark, and this is B mark. Part B says a sample contains n naught nuclei of carbon 11 and no other nuclei at time t is equal to 0. On figure 9.1, sketch the variation with time t of the number of nuclei of boron 11 in the sample. And half-life of carbon 11 is also given to us in part A. Half-life is equal to 20 minutes. So these informations are given to us. So in this case, we need to understand we have initially n naught. After one half-life, we will have n naught by 2, and after another half-life, we will have n naught by 4, and after another half-life, we will have n naught by 8, and so on. So it simply means that when t is equal to 20 minutes, we have this one. At t is equal to 20 minutes, we have n naught by 2, and at t is equal to 40 minutes, we have n naught by 4, and at t is equal to 60 minutes, we have n naught by 8. So simply, first of all, we have n naught by 2, so here we have n naught by 2, and then we have n naught by 4, so here we will have n naught by 4, and then we will have n naught by 8, so the half of this, so we have 1, 2, so it will be somewhere here, then half of the remaining, so we will have about this. So first of all, you can mark these points, then simply we need to connect. So this is how we can connect. So very straightforward question, but this is a kind of typical question you will see in many past papers about nuclear physics. Part C says explain with reference to the random nature of radioactive decay why the activity of carbon 11 sample in B decreases with time. This is a pretty straightforward question. Let me explain you in a very simple way. For this one, you need to understand that activity, this is equal to minus, we also use in front of lambda. Minus simply tells us that number of nuclei decrease with time, but most of the time in physics simply we write down A is equal to lambda n. Lambda here is decay constant, so you need to understand the meaning of these symbols. Lambda is representing decay constant, and this is the probability of decaying of a particular nucleus per unit time, and each nuclei in the sample has the same probability to decay, so lambda is a constant. N is the number of nuclei remaining in the sample, or we can say number of undecayed nuclei. So very important one to understand, number of undecayed nuclei in the sample. As time passes, number of undecayed nuclei in the sample go down. As these number of nuclei go down, activity also go down, because this is constant. So these are the points you need to understand to answer this question. Let me show you the answer, how you can write down your answer. This is how you can write down your answer. Simply you can say every undecayed nucleus has the same probability of decay, means lambda is constant for each nuclei. So this is 1 point, so we can say this one is 1 point. Fewer undecayed nuclei remaining with time, so fewer decay, so it means activity decrease. Mean as time passes, number of undecayed nuclei decrease with time, and activity depends on number of undecayed nuclei in the sample, so activity also decreases with time. I often used to tell students lambda is like a constant, so this is decay constant. We can also understand this one. On this planet we have around 7 billion people, and each person has the same probability to decay, or we can say same probability to die. So we don't know who will die next, but everyone on the planet has the same probability to die. Second part says, state with reasons whether a radiation detector placed near to the sample of carbon-11 indicates a measured count rate from the sample that is less than, the same as, or greater than the activity of the sample. So first of all, we need to understand what is difference between count rate and activity. So first of all, let's try to understand the difference between count rate and activity. Count rate simply is the number of radiations, we can say number of radiations detected by detector per unit time. Detected by detector, we can simply say per unit time, and activity is, activity we can simply write on here, activity is the total radiation, total number of emitted radiations per unit time, emitted radiations per unit time, emitted radiations per unit time. So this is in a simple way how we can define activity. So activity is the number of radiations emitted, total number of radiations emitted per unit time, and measured count rate is the number of radiations detected by detector per unit time. If we have this understanding, I hope simply now you can say that count rate in this case has to be lower than activity. So this is what we can infer from this, if we have understanding what is activity and if we understand what is count rate. Now we need to understand why count rate is lower than activity. In this case, we have this sample. So this is a piece of radioactive substance. It will emit radiations in all possible directions. So it will emit radiation this way, it will emit radiation this way, it will emit radiation this way, it will emit radiation this way. Means in all possible directions, it will emit radiations. But the number of radiations emitted by the detector, those radiations are only coming straight to this detector. Other radiation, for example this one, they will not be detected by detector. These radiations also will not be detected by detector. These radiations also will not be detected by detector. So from here you can see that count rate has to be much less than activity. And also when radiations are emitted, some of the radiation, they are absorbed by air. And it is also possible some radiations are absorbed by the window of this detector. And also this detector, maybe it is not very efficient, so it will have some dead time. Means in that short period of time, this detector will not be able to record radiations. So these are the reasons why count rate is lower than activity. Let me show you the answers so you can have better understanding and also you can write down your answer. So these are the points you can mention in your answer for this question. This question has 3 marks, so you can write down any 2 of them. 1 point, you can say sample emits in all directions, but detector only captures emissions in one direction, as we have mentioned here. Some emissions are absorbed before reaching detector, means they are absorbed by air. Some emissions are scattered within the sample, we can also write down. So this is 3rd point. Simultaneous arrival of multiple particles only registers 1. Mean many particles, they arrive together, but this detector will count 1. So Meyer count rate is less than activity. We can also say maybe some radiations are absorbed by the window of detector, or you can say GM tube. So these points you need to understand, and this question is also common question. In question 10, part A says state Hubble's law. Identify any symbols that you use. Hubble's law is a very simple law. We can simply write down first of all Hubble's equation. V is equal to H naught T. H naught here is Hubble's constant. So this is Hubble's constant. Hubble's constant. So from here we can simply say that V is directly proportional to T. V is the speed of recession, or we can say recessional speed. So V is speed of recession. So this is speed of recession, and D, distance of galaxy from the observer. So this is distance of receding galaxy from observer. Galaxy from observer. So these things you need to understand to answer this question. So for this question, simply we can say that speed is directly proportional to distance. So if you write down this one, you will get 1 mark, and this 10 mark, mean it has to be in your answer, otherwise you will not get a mark. And speed is speed of recession, and distance is the distance of galaxy from the observer. If you write down these 2 points, you will get 2 marks. Part B says a star of luminosity 3.8 times 10 to 31 watts is the distance of 1.8 times 10 to 24 meters from the Earth. Calculate the radiant flux intensity at the Earth of the radiation emitted by the star. We need to calculate radiant flux intensity, means we need to calculate F. And in this case, power, luminosity, means the total power emitted by the star is given to us. We need to calculate flux intensity. So simply for this question, we need to understand that F is equal to L divided by 4 pi d square. L is the luminosity, this is the power emitted by the star. We have power emitted by the star, that is equal to 3.8 times 10 to 31. And here we have 4 pi, and we have d squared. The distance between star and our planet is given to us. That distance is equal to 1.8 times 10 to 24 square. Now if we solve this one, we will get our final answer, that will be equal to 9.3 times 10 to minus 19 watts per square meter. So it simply means that if we take 1 square meter area at the surface of our planet, the power we will receive in 1 second, that is equal to 9.3 times 10 to minus 19. Because when this star, as this is emitting energy per unit time, this energy will spread over this surface area. As the distance get larger and larger, energy per unit area will go on decreasing. So intensity depends on distance, but luminosity of the star, means L, the luminosity of the star, this is intrinsic property of the star, and it does not depend on distance. So in this case, energy, first of all, you can simply imagine it was close in this area, then it goes to this one, then go to this one. So energy spread over larger and larger area. So the energy per unit area will go on decreasing as distance increase. So intensity depends on distance, but luminosity does not depend on distance. So this is how you need to answer this question, and this question has 2 marks. First mark, you will get C mark if you have written this equation, and the second mark is the answer mark. If you got the right answer, you will get 2 marks. Part C says the star in B is in a distant galaxy. A spectral line in the light from this galaxy is known to have a wavelength of 486 nanometers. This spectral line in the light from the galaxy observed on the Earth has a wavelength of 492 nanometers. Explain why the wavelength observed on the Earth is different from the wavelength that the galaxy is known to have emitted. So in this case we have lambda emitted by the galaxy. So this one is lambda emitted. Lambda emitted is equal to 486 nanometers, and lambda observed in this case we have that is equal to 492 nanometer. So in this case lambda observed, this is greater than lambda emitted. So it simply means that it is red shift, means the light is red shifted, and red shifted means that moving away. So galaxy is moving away from our planet, so this is moving away. So these are the points you need to understand. So you need to understand these 2 points. Lambda is greater, so it means the light is redshifted from the galaxy, so it means galaxy is moving away. So these 2 points you have to mention for the first part. So in our answer we can write down these 2 points. We can say galaxy is moving away from the Earth, wavelength of light. Then we need to explain why. So here we are explaining why. Wavelength of light from the galaxy increased by the Doppler effect, or we can say it is due to red shift. So you will get 2 marks. For the second part we need to determine value for the Hubble constant, and we understand Hubble equation means V is equal to H naught D, but value of D already was given to us in part B. So if we can have value of V, we can calculate H naught. So H naught simply is equal to V divided by D. V is the speed of galaxy. In order to calculate speed of galaxy we can use delta lambda by lambda. This is equal to V divided by C. Lambda is the change in wavelength. In this case wavelength increased, so will be writing here lambda observed minus lambda emitted divided by lambda emitted. Emitted means the lambda of light emitted by galaxy. So here we have V, we need to calculate V, and C is a constant, it has constant value. Now from here if we simply plug in values, we will plug in values here. So we can write down lambda observed, this is lambda observed, this is lambda emitted. So we can write down 492 minus we have 486, and here we have V, and this is divided by 486. Lambda emitted divided by C. C is equal to 3 times 10 to 8 meters per second. If we solve this one, we will get value of V. Value of V in this case will be equal to 3.7 times 10 to 6 meters per second. So we have value of V, simply we can plug in here. We have 3.7 times 10 to 6 meters per second divided by value of D. Value of D was given to us 1.8 times 10 to 24, and if we solve this one we can find out value of Hubble's constant. So here we will get our value of Hubble's constant. Hubble constant in this case will be equal to 2.1 times 10 to negative 18, and the unit of this one is per second. So we can write on this is 2.1 times 10 to minus 18 per second. So this is how we can calculate this question, and this question has 3 marks, means this is the answer for this question. The first mark you will get if you have got the right value of the V, you will get 1 C mark, and the second C mark you will get if you have written this equation, and the third is the answer mark. If you have got the right answer, you will get 3 marks. So that's all for this question. I hope this video was helpful and you have better understanding of astronomy and cosmology. And also I hope you have better understanding of this whole paper if you are watching all the questions from this paper. If this video was helpful, Please like and subscribe because your encouragement is very important. And also, if you have any questions, please leave your questions in comments. I will try to answer as soon as possible. See you in next video.